section 322. So we just solved the potential for this by just writing down an equation that happened to solve the boundary conditions for a completely different problem. And so let me just kind of recap. So we have a charge plus q, a distance d over some infinite plane. It goes on forever. Okay. So, and the potential at the plane is 0, the potential at infinity is 0. So, and then we have the solution that the potential is equal to 1 over 4 pi epsilon naught q over square root of x squared plus y squared plus x minus d squared minus q over the square root of x squared plus y squared plus x plus d squared, which is the same potential for if we had solved the problem. We had plus q up here and minus q down there, distance d. Okay. So now that we have the potential, we can calculate sigma, the surface charge density on the plane. And so we have this neat little equation that says the derivative with respect to the voltage, the potential, over the normal of a conductor is simply equal to minus sigma over epsilon naught of the surface charge density on that conductor surface. And that came from section 2.53. If you want to review that video, you're certainly encouraged to. Write that down. Okay. Now, in this case, the normal is z, right? So this is the same as saying, I'm going to use a lot more room over here. dv by dz is equal to minus sigma over epsilon naught. And we're solving for sigma, so basically sigma is going to be equal to minus epsilon naught dv by dz, which, when we differentiate this, we get epsilon naught 1 over 4 pi epsilon naught. And let's be careful with our derivatives here. I actually took more time than I care to admit solving this one. So we're taking the derivative of something over something to the negative 1/2 power. So we have negative 1/2 times q over that thing, x squared plus y squared plus x minus d squared, times the derivative of this thing in the middle. So that's 2 times x minus d. And these 2's cancel. And we subtract negative 1/2. Oh, this is actually to the negative 3/2. Okay, so now we have negative 1/2 times q minus a minus, so a plus, basically. This is messy. I'm sorry about this. X squared plus y squared plus x plus d squared, the 3/2. We take the derivative of this, so that's just 2x, so these 2's cancel, so we just get qx plus d, I'm sorry. And the derivative of z. Okay, I've completely botched this one, but I think it's salvageable. You'll still understand what's going on. The reason why I'm so, I'm actually excited. I love the conclusion of this theorem. And we're going to talk more about kind of its implications in a bit. So basically, we simplify these. We get, so we have a minus z and a plus z, so these z's cancel. So we have minus minus d, so we have a plus qd on top here. And we have a plus qd over here. And we're looking at the surface, so we set z equal to 0. So we get minus epsilon naught 1 over 4 pi epsilon naught. So we have plus qd over x squared plus y squared plus, well, 0 minus d squared. Well, that's just d squared. X squared plus y squared plus 0 plus d squared. That's just d squared. So we get x squared plus y squared plus d squared to the 3/2, which I think is in agreement. So let's cancel out some terms. So, all right, I'm panicking right now because I see a plus. Where did the negative sign come from? So we had negative epsilon, negative q, negative 1/2. That's definitely positive. That's positive. Where'd my negative signs go? I don't know. negative q times negative d, negative q times z. This one was negative and negative. This is positive. It's positive q times z, positive q times d. So we get 2 qd's. We get 2 of these, and it's positive, and that's negative. And that's not supposed to be... Oh, no, no, it is. Yes, I'm right. I am so right. It is supposed to be negative charge to counteract the positive charge. So my notes were wrong, yet again. And so we cancel out some terms here, cancel out that and that. We cancel out a 2 here. I kind of want to keep that. I like that too. No, he's gone. 5, 2. Okay, it's equal to q d over 2 pi times x squared plus y squared plus d squared to the 3 halves. Okay? And so when the maximum for this occurs when the minimum denominator occurs, which is when you have x and y to be 0. So right in the center there you have the maximum charge density. And outside, so see, it should be, yeah, that's right. Squared, yeah. Okay, I'm just checking the units here. So you have squares of distances. Square root, so that's distance cubed, and you have distance on top, so it's over the distance squared, which is, charge per unit area. So it creates this kind of shadow, circular shadow effect, which basically starts here, maximum at the surface, then it kind of spreads out in a circle. Okay. Now, suppose we want to calculate the total charge. I'll just do this over here. It's a quick calculation. So this is just the same as sigma dA. So we could do it in Cartesian coordinates, but I'm going to do it in circular coordinates, substituting. And I do need a new piece of paper actually. So let's do that. So we have Q equals the integral of the surface charge density times the area at the point that the surface charge density integral is. So we have r squared is equal to x squared plus y squared. And theta is uniform, so then our dA becomes r dr d theta. And so then we have Q equals the integral of sigma, where we're substituting r squared for x plus y squared, so you have q d over 2 pi r squared plus d squared to the 3 halves. And the dA is r dr d theta. And we break this out, so there's no theta components here, so we just have d theta. And then we have integral of q d r dr over 2 pi r squared plus d squared to the 3 halves. And so this becomes 2 pi because we're doing all the angles. So we can just basically cancel out 2 pi over 2 pi. Pulling that out, q is constant, d is constant, everything else is not. R dr over r squared plus d squared to the 3 halves. So we're going to do substitution. And for funsies, I tried several different substitutions. The one that I liked the most was when I substituted u is equal to 1 over the square root of r squared plus d squared. And so du is equal to the square root of that, so it's negative 1/2 times 1 over r squared plus d squared to the 3 halves. And you have to take the derivative of the inside too, so you get the 2r at the top dr. Wow, that's like exactly the same. So basically these two cancel, except you got a negative sign there, which should have appeared because the charge is negative. After all that work talking about the negative charge, I forgot to write it down. Okay, so it is negative. Negative, 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 negative. Okay, so our du is equal to minus r dr over r squared plus d squared to the 3 halves. So we get equals to, different color. QD, the integral of du. Isn't that beautiful? And that becomes equal to QD, well, the integral of du is just u, evaluated between, well, we're going from r equals 0 to infinity, so we kind of need to substitute in there. So we get QD of 1 over square root of infinity squared plus d squared. And we get minus 1 over the square root of 0 squared plus d squared. It's a square root, okay. And so as you can see, this one's going to go to 0, and this one's going to go to 1 over square root of d squared equals 1 over d. Okay, so we get equal to QD. This negative sign goes up here, so it's negative Q. Where did the Q come from anyway? Oh, that's the original charge. Oh, ha! I'm done. Yet another surprising result. So I guess now that you see the result that the charge on the surface is negative the charge above the surface, it kind of sounds like, oh, of course it has to be that way. And that's pretty much all there is to that. So that was kind of fun.